All right, we are going to be on this page here. Like I said, we're kind of going a little bit out of order. I kind of switched things around last week and we moved circles and that forward. So we're going to go back now to these regular polygons. So make sure you're on the right page. It should just say like polygon investigation at the top, part 1. So today and tomorrow, we're going to spend time looking at how we would find area of a regular polygon. What that means, when something is regular, that means that all the sides would be the same length. So when we talked about quadrilaterals in the past, like we spent last week talking about rectangles, parallelograms, trapezoids, like none of those shapes are considered regular because they don't have all equal sides. Now a square would be regular because a square has all 4 congruent sides. But if we have something that has 5 sides or 6 or 7 or 8 or 9 sides to it and all the sides are the same, that would be called a regular shape. So think about like a stop sign. Okay, a stop sign has 8 sides. That would be an octagon. But all 8 sides of that stop sign are equal. So that would actually be a regular octagon. So those are going to be the shapes that we focus on today and tomorrow. And we're going to talk about how do we find area of those. Because after quadrilaterals, they kind of stopped creating formulas for each individual shape. If we did have a formula for every single individual shape, we'd have a lot of formulas to have to try to remember, okay? Because you'd have one for a pentagon, a hexagon, an octagon, a nonagon. Like you'd have all these different formulas that you have to remember and keep track of. So they kind of have one formula that we can use for any regular polygon, and that's what we're going to kind of get into. But before we get too far into that, I want to talk about how you discover how many degrees are inside of these shapes. Okay, last week we talked a little bit about like degrees in a circle. When we were working with the sector, we said that a circle has 360 degrees in it. How many degrees does a triangle have in it? 180. Do you guys know how many degrees like a quadrilateral would have, all quadrilaterals? They would also have 360, okay? But now as we're getting into regular polygons, we need to know how many degrees are in those shapes too, because that's going to come into play, especially tomorrow. So to do that, I want us to take a look at our notes here and start answering some of these questions. So this first one we just talked about, how many degrees are in the angle sum of a triangle? You guys said 180 degrees. Okay, that's something that we're familiar with. We've used that a lot to help us with problems in the past. Okay, what they're saying though is if you guys know that, if you know that there's 180 degrees inside of a triangle, then you can use that to help you find the sum of the interior angles in any polygon by just cutting that polygon up into triangles. So even when we were working with like a rectangle and we drew in those diagonals, we were creating triangles inside of that rectangle. We were able to then see there's 2 triangles. So those 2 things added together would be that 360 that we talked about. So if you look at this first one, we've got this kind of random quadrilateral here, A, B, C, D. And they drew in a dotted line to kind of almost like be that diagonal that we've talked about. And it creates 2 smaller triangles in there. So if we look at the 2 smaller triangles, one of them would be angle 1 plus 2 and plus 3. What would those 3 angles equal? $180, because that's one side of the triangle. What would angles 4, 5, and 6 add up to? 180 as well, because it's another triangle. So then they're asking, all right, if you know that those individual pieces like add up to 180, if you were to add all of those angles together, so angle 1 all the way up to angle 6, how much would that be? 360. Okay, and so we kind of talked about that earlier already, but all quadrilaterals, no matter what it looks like, if it has 4 sides, if it has 4 interior angles, the sum is always going to be 360. For this shape, that would mean like all of angle A plus all of angle B, all of C, and all of D would equal 360 degrees. Not so much of like the 1, the 2, the 3, because some of those aren't going to be an entire interior angle anymore. I'm talking about all the corners of your original shape before you drew in any of the diagonals would add up to 360 for a quadrilateral. Okay, now as we add more sides to our shape, the sum of the interior angle should also increase. Okay, but I want us to see if there's any type of like pattern or reason why it increases by a certain amount. Okay, so now let's take a look at this next shape. This one's a pentagon. Pentagon tells you that there's 5 sides to it. So A, B, C, D, E is our new shape here. I want to draw in my triangles. Now it gives you a hint here. It says from one vertex, draw all possible triangles. So they don't want you to draw like all sorts of diagonal lines in here. I could create a lot of triangles in this shape if I really wanted to. What they want me to do is pick one letter to be my vertex, and that's going to be where I draw all my triangles from. So I'm going to pick B, and I'm going to draw triangles coming from point B. One that I'm going to do is going B down here to E. I don't want to draw B to A because those are already connected. That's not going to really show me or help me with anything. Where else could I connect B to create another triangle? To D. Are there any other triangles I should draw on this one? Again, if I try to connect B to C, that's already on the outside edge. That's not really going to be helpful to me. So I don't think I have any more points to go to. So how many triangles did I create there? 3. Okay. I could go in and label all those corners of the triangles, but we know the degrees in all 3 of those triangles are going to add up to what? 180. So I have 3 triangles this time. So I have 3 sets of 180 degrees. So what would be all the sum? Not 360. That's a little too big. 540. How did you get that number? How'd you get 540? You took 180 times 3 because there's 3 triangles. They each equal 180 degrees. So we just did a quick multiplication there. And that's 540. You could also add 180 plus 180 plus 180. Okay, and you would still get 540 degrees. Okay, now let's take a look at the last one on this page. Now I have a hexagon. Hexagon means 6 sides. Okay, again, let's pick a letter to draw all of our triangles from. What letter would you guys like to draw our triangles from? B again? So what letter should I connect from B? B should go to what? F. And D. Good. Oops, that one got a little off. How many triangles did we create there? 4 this time. Again, there's 180 degrees in each triangle. So this equals, what did you say a little bit ago, Dash? 720. And where did we get that number from again? 180 times 4 is 720. Okay, so can you guys, before we go to the backside, can anyone make a generalization about the process here? If I had any shape out there, what could I do? Which is what?
Use one vertex in the triangle and then multiply 180 times 5 and then triangle.
Okay, so let's even just think about this before we go to the next page. The last shape we had there was a hexagon. Okay, that had 6 sides. Let's go to an octagon. I'm going to skip over 7. Okay, so octagon has how many sides? 8. How many triangles do you think we would be able to create instead of an octagon if we were able to create 4 in a hexagon? 6, because I skipped over the 7th shape, okay, the 7-sided shape. So then if there's going to be 6 inside of an octagon, I would need to take 6 times what? 180 to get to its sum, okay, for all those angles. So I'm hoping you guys notice, like, as we add more sides, like every time we add a single side, we add another triangle possibility. So we add another combination of 180 degrees. Okay, so let's turn our sheet over now. If you guys look at the top of this next page here, there's this big chart. We're going to fill this out. Okay, we've kind of talked about how there's this pattern that's developing as we talk about these shapes. We're breaking them into these triangles, and then we're able to kind of see what that's doing with their sum. They already have triangle filled out for us because triangle is kind of the shape that we've been using to help us do this. So that's kind of where we start. Triangle has 3 sides. It has 1 triangle because that's what the shape is. So the sum would be 180 degrees. That's something that we've talked about already a lot. Quadrilateral, how many sides does a quadrilateral have? 4. We were able to create on the back page there 2 triangles, and we said that the sum was 360. Okay, a pentagon had how many sides?
5.
And how many triangles did we create? 3. And we said the sum was 540. This is all from the previous page yet. Okay, a hexagon had 6 number of triangles.
4.
720. Okay, if we keep filling out our chart here, the next shape that they have is heptagon. That has 7 sides. How many triangles would be in there? 5. What would be that sum?
900.
Good, 900. Octagon, we talked about this one, has 8. So there'd be 6 triangles in there. So if you take 6 times 180, what do you get?
1080.
Good, 1080. Okay, nonagon means 9. There'd be 7 triangles that you could draw inside of a 9-sided shape. What's the sum of the angles?
1060.
Good. Okay, we're getting close to the end here. Decagon is 10 sides. A dodecagon would be 11 sides. I'm sorry, not 11, 12. We skipped over 11. I'm actually going to add that over here. I'm just going to draw a line right here. 11 sides is called a hendecagon. All right, so back to the decagon. How many triangles would be inside of that? 8. What would be that sum?
1001.
Good. Okay, we skipped over the 11 sides shape. I kind of added that off to the side there. That would mean there'd be 9 triangles in there. What would that sum be? Yep. And then the last one here, back to that dodecagon, the 12 sides, that would have how many triangles on the inside? 10. And so its sum would be
1800.
good. All right. Now, after 12, they stop giving the shapes fancy names. Okay, so after dodecagon, so when you get to something that has 13, 14, 15 sides, they stopped calling them specific names because, again, if we did that, we'd have a name for everything. And that'd be a lot to try to keep track of. So after 12, anything bigger than that is just called the number of sides it has dash gone. So, for example, you'd have something like a 15 dash gone or 17 dash gone. That just tells you how many sides it has. They stopped giving them fancy names. Okay, there are times where you maybe have to work with something like that, and you might even see that on a problem where they just want you to find the sum of the angles. They're going to tell you how many sides it has written like that. They're not going to give it a special name. Now, what I want us to do is using this information, you guys are starting to recognize a pattern here. We want to be able to write out a general formula that we could use for any shape. So even if I had 100 sides that I wanted to work with here, if I had a 100-sided shape, I would want to maybe find the angles inside of that. I should be able to just plug into a formula instead of having to think about, okay, I got to add this many triangles or whatever. So when we had the number of sides, they call that n because n could represent however many sides that your shape has. How would you relate the number of sides to the number of triangles? We subtracted 2. So how would we write that down here? Good, n minus 2. And then after we found the number of triangles, so like the 1, 2, all the way up to the 10 there, what did we do with that number to get our sum? Times it by 180. So over here, I'm going to write that like this, n minus 2 times 180. That would allow me to find the sum of interior angles of any shape. So if I had something that had 30 sides to it, I would put 30 in for n. So you take 30 minus 2, you're down to 28. You would take 28 times 180. That number would tell you what the sum of those interior 30 angles would be. Okay? Now again, let's talk about the difference between regular and non-regular. I went over this a little bit at the beginning of class. A regular polygon, if you look at these pictures here, looks like the one on the left. Notice how all the sides have those dashes through them. That's telling you that all the sides are congruent. It also has those arcs drawn in on all the angles. That's telling you that all the angles would be the same amount as well. So when you're working with a regular shape, not only are all the sides equivalent, but all of those interior angles are going to get the same amount. So if I had a square, because square is a really easy shape for us to think about. Square is a regular shape because all four sides are the same. How many degrees are all four angles in a square? 90 degrees, okay? Now, if I'm working with this pentagon here, all 5 of those sides would be the same amount, and all 5 of the interior angles would be the same as well. So I would be able to take that sum and cut it equally 5 times to tell me how many degrees each corner is going to get. Okay, so when they're saying, describe what's required for a shape to be described as regular, we would probably say that all the sides and all the angles are equal. Do you guys understand why the one on the right is considered non-regular? It doesn't look like all those sides are the same anymore. Some look longer than others. And it also is showing you that some of those angles are different too. They're not all going to be the same amount. Some of them are going to be smaller, some of them are going to be bigger. It just kind of depends on what kind of shape you have here. All right, so then they're going on to ask some like specific questions about the regular polygon here. What's the sum of the measures of any pentagon? Well, we would use our formula that we talked about up above, which was 5 minus 2, because that would be your n. N would be 5, because it's a pentagon, times 180. What did we say that sum was? 540. So up on my shape there, A, B, C, D, and E, if I add those all together, I get 540. What would you do if you just wanted to find one of the angles? Divide by 5. So we would take 540 divided by 5. How much does one angle get? 108? Okay. They're asking, what's the measure of one angle of that non-regular polygon? Would you be able to figure that out? No, we don't have any information about that. So we really can't answer number 4. I'm just going to say we can't do this. We need more info. I would need to know the relationship between those angles. Like, are there any that are the same? Are they all totally different? Or I'd have to know most of them in order to figure out a way to solve them. Or if they gave it to me as like an algebraic expression, I'd have to add all those pieces up, set it equal to the sum, and be able to work backwards that way. Okay. They're asking then for number 5, describe how to find the measure of each angle of a regular polygon. So any regular polygon, you would take the sum of your angles, so your interior angle sum. So that'd be all those numbers on that last column of that chart from up above, that 180, 360, 540, 720, 900, all those numbers. Those are your interior sums. We would divide that by the number of sides or angles. The angles and sides should be the same on a regular polygon. So it doesn't really matter if you're thinking about sides or angles because it should be the same number. Okay, so the last thing we have here is another chart to help us just figure out what would be the sum of some of these regular shapes that we're going to see a lot. So when we're dealing with hexagons, pentagons, those kinds of shapes, we should be able to know how much an angle is going to be. This would be really useful for us, especially tomorrow when we continue to talk about regular polygons as well. So we said earlier that in a triangle, the sum was 180. Let's just go ahead and fill in our sum for all of these here. We said a quadrilateral was 360. Okay, and then I'm just going to keep filling in these numbers. This is all from that last column up above. Again, take note that they are skipping over the 11-sided shape again here. They just went straight from 10 to 12 on my chart. Now I want to find the measure of each interior angle. So you're going to take the sum that we just wrote down and you're going to divide by the number of sides. So a triangle has 3 sides, so what's 180 divided by 3? 60. What would be 360 divided by 4? 90. 540 divided by 5? 108, we did that earlier. Okay, now we're going to keep filling these in. So what would be my next one? What'd you say? 120. Next one.
28.5.
0.5 what?
7.
So I'm going to round it up to 6. Sometimes they're not going to come out nicely because you can't always divide the sum evenly. Okay, next one.
135.
Next. 140. Next one. Good. Good. Okay. So an n-gon, that would be any side shape out there. We've talked today now that the general formula to find the sum is to take n minus 2 times 180. So if that n was a 20 or a 30 or a 40 or a 50 or whatever, and then to find the measure of each interior angle, we take that same equation, n minus 2 times 180, and we divide by n. And that'll get you a single angle from that shape. All right, do we have questions on angles of polygons like that?